you need like a jump from 4 to 2 to be in the visible range. There's a bunch of jumps that are high enough in energy that they're out of the visible range and you can't see them. Or they're low in energy so that you can't see them. But there are several of the jumps that are right in the right energy range that are visible to us. I have just one last slide for today, and that's this one. Bohr theorized that those electrons can only exist in certain energy levels that have only certain distances from the nucleus. And he used an equation to calculate the energy of an electron. Am I doing it again?
No, not at all. Keep going. No.
I was going to finish this one anyway, but yeah, that's good.
What were you doing again? What was happening again?
Nothing, we're just talking. So Bohr recognized a pattern in the amounts of energy, and he was able to come up with this relationship. And it works perfectly, but it's unfortunately only perfect for hydrogen. It doesn't work for any other element. To be honest with you, I don't even know why we learn about the Bohr model, because it's only good for 1 out of 110 or so elements. But it was a pretty big deal, and it was the first attempt at a theory that described electrons using the quantum theory. Now, underneath this shade here, I've got what the variables represent. E, of course, is energy. Z squared, that would be, Z represents the atomic number. So for hydrogen, which is the only equation that we can use this for, Z is 1, the atomic number. And then the N value is what energy level. N equals 1 is close to the nucleus, and then as we go up, it gets farther and farther away. And it gets higher.
Wait.
And something might be troubling about this equation.
Yeah.
What are you troubled by, Patrick?
Why would they put a Z squared if there's only 1? If you can only use 1, I guess. Because it's always going to be 1 anyway.
Bohr, I believe, was thinking at the time, he was using hydrogen but assuming that it would work for others. I don't know exactly how Bohr derived this thing, but yeah, he was probably trying to generalize it and say atomic number squared, which it didn't work for others. Yeah.
So Z does not have any unit?
No, neither does it. Right.
Oh, yeah.
Wait, why did they put it out there in the first place?
We're always going to use 1 for this thing, so you don't have to call it Z squared. This is the Bohr equation. Like I say, I think he was aiming for this equation to describe all elements, but it doesn't. Now, what I said just a minute ago was something might be troubling. Any of you look at that negative sign and feel troubled by it?
Negative energy.
Negative energy doesn't really have a meaning, does it? We're really, though, concerned about delta E, an electron jumping from one energy level to another. When an electron has a low energy, that means it's more negative. And that sign has to be, that negative sign has to be there because when we start calculating delta E for electrons jumping, it will give us the right sign as long as the negative sign is here. Can you see my rings over here? I have an atomic model. This one I like better than this one because this doesn't accurately describe the electron's energy levels. The the energy levels start far away from the nucleus, and then as you go out, they get closer and closer to each other. That's not really what we see happening here. This is more more accurate in terms of the farther out you get, the closer the rings get to each other. Can you see it? How they're getting closer to each other? You guys over here can see it. When you have an electron falling from a higher energy level to a lower energy level, it's giving off energy. With the negative sign here, if an electron is falling closer to the nucleus, the delta E will be negative because it's losing energy. If an electron jumps from a low energy level to a high, the delta E will be positive. As long as we keep this negative sign here, when you have changes in energy, you'll get the right sign for the change. And you have to have that negative in there. So you'll appreciate the negative when you do a few problems. And there are definitely a lot of problems that you'll have to do with the Bohr equation. Wouldn't be surprised if it shows up on the quiz. Where you'll have to calculate the electron energy jump from like the 4th energy level to the 2nd energy level, or the 3rd to the 5th, or something like that. You'll have to do jumps. So we'll try an example tomorrow. Before we quit though for the day, I asked you to hang on to your glasses because I do at least want to show you, while I have this chart